Okay, for those who are joining in on the stream, I've just arrived, so I should be up and ready in about less than 5 minutes. Bear with me. Yes, it's me. Interesting. It looks like the smart board doesn't seem to work. Interesting. That's fine. Maybe I'll drive it with pen and paper. It says doc cam not available. All right, I have to get this fixed for the next lecture for sure, but it looks like the doc cam isn't working. The annotation isn't working, but hopefully I'll try and see if I can guide the intuition in some other way. Okay. So semester 1, 2023, welcome. So my name is Arun Konogurtu. I've been in the faculty for quite a while. I've been here since last at least 14 years. I've taught several courses. I've taught the 2004, the version that you've done in at least most of what you've learned in 2004 was something that I designed in 2014, year 2014 until 2017. In 2018, I took the task of developing the advanced data structures and algorithms. So that's the unit that we are currently in. What I'm going to do is not spend the first 20 minutes giving you an overview I'd like to flip this thing by first starting with an algorithm, and towards the end, we're going to cover some aspects about the housekeeping of the unit. How about that? Okay? All right, so I just want to say that the first quarter plus of the unit would be about string algorithms and string algorithms and data structures, mainly geared for efficient search and retrieval. And this topic, Gus Field's Z algorithm or Z algorithm, however you want to pronounce that letter, is of that kind. It is sort of a data structure if you think about it. And it's a data structure that allows you to do efficient pattern matching on strings. And we will qualify what efficient means as we chug along. Okay? So we'll start with Z, and then we'll go to what are historical algorithms, algorithms that really started at the real onset of computer science as a field. I mean, I guess it's easy to forget that computer science is not such an old field of activity compared to other traditional sciences. Computer science is far more recent, right? So up until mid-70s, it used to be a small niche in a mathematical department, and then with the importance of computing growing, you started seeing computer science department pop up across universities around the world. So Boyer-Moore and Knut Morris Pratt, all those names are names of some of the phenomenal mathematicians who were forefathers of the algorithmic way of thinking in computer science. They came up with some of the earliest efficient algorithms, but then for pattern matching on strings. So if you we'll see what that means in a bit. But the idea is that we're not just going back and looking at those algorithms. Gus Field's Z algorithm is a turn of the millennium in late 90s, early 2000s. I think the paper was in 1998. It's a tech report. That arose about 20 years after Boyer-Moore and Knut Morris Pratt. But then it reflects, we could use this new data structures and do Boyer-Moore and KMP a bit more, in a much more watertight way, perhaps. Not perhaps, but surely a better way. Okay? So that's the agenda. So what are we going to learn this week will have impact on your learning of Boyer-Moore and KMP next week. So please make sure that you understand this algorithm, at least after you listen to it, and then come back to it during self-study so that while you come into the next lecture, you at least know what we're talking about. Okay, source material. Most of my slides will accompany as reading material. In some weeks, we will give you reading material scribed by one of my tutors, Taylor Kearney. So there'll be some reading material accessible, but if you stuck to just the slides, it'll contain all information that would be examinable, but always think that learning happens by reading over and beyond. Okay. So far, so good? Okay, thank you. Okay, what's pattern matching? It's quite easy. You have a reference text, often a long one, right? Huge reference text. When I say reference text, it could be a collection of text too. So it could be like you're searching something, it's a collection of documents, isn't it? So let's assume that in our worldview, everything that you want to search is a long concatenated piece of text, and you have a pattern, you want to find all occurrences of the pattern in the text. Does anybody have any confusion about the problem we're dealing with? Okay, you have a text, you want to find, I want to find Arun in a set of documents. My pattern is ARUN, and my text is basically this long concatenated piece of text in the documents, let's say, and then you want to find all occurrences of Arun in that reference text. Okay? And obviously that example, I don't have to explain that example. It's essentially trying to have the text at the top, and it says that this pattern ABA appears at position 3, ABA appears at position 7, ABA appears at position 9. So 3 occurrences of ABA in the reference text. Clear? Okay, so we can see why this problem arises in numerous applications. Maybe it's a starting point, sometimes we misspell and stuff like that, but for the moment, let's assume that you're doing just the exact pattern matching, okay? So if you did a naive algorithm, I don't have to sort of clarify what the pseudocode is. I mean, I'll write pseudocode in some ways that are not exactly Python, because pseudocodes are meant to be general, but it kind of captures the logic in some form. So it's a combination of something that looks like a computer code, but you can't just copy and paste it. You still have to make it work if you have to talk to a computer. And then it'll be a combination of some English, that is plain English, that you could follow while you're reading it. So what you're essentially doing in a naive algorithm is you're exhaustively sliding and comparing the letters of the pattern against the opposing symbols in the text one by one. So you first put pattern against the first symbol of the text, the first character match, the second character match, the third character match, and so on until you find a mismatch. Well, if you found a mismatch, well, too bad. I couldn't find the pattern at position 1. So what do? I slide by 1. Now the pattern is aligned with position 2, and then say, does the first character of pattern 1 match with the second character of text? The second character of pattern match with the third character of the text? So you're essentially doing a comparison one by one. And when do you print that you have found an occurrence? When you have exhausted all letters and all letters were matches. Match, 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 and you reach the end of the pattern has ended, so you found an occurrence. Clear, everyone? Okay, this should be obvious. So what's the complexity of such thinking? So if you have a reference text of n letters and a pattern of m letters, it's easy to see in a pathological case that you will end up having an effort that is big O of m times n. Can you see that in the naive algorithm? So you're essentially putting the tick marks is the number of comparisons you have to do. Okay? So if you have the pathological case is when you have the same letter repeat in the reference text as well as the pattern, and you would compare every single letter, every Cartesian product of the letters in the pattern and in the text. So that's going to be quadratic, isn't it? M times n, so it's kind of a lot of wasted effort. Take your time. Now, we saw a pathological case, but we also see some cases where a general case, a bland case, where you have some text that's not necessarily periodic or repetitive. There's some amounts of some patterns in it. Let's say that that's the text at the top. I'm sorry, I can't annotate it for those who are joining in online, as well as those who are here. I can't really annotate it because the document camera is not working, the smart board isn't working, so I'm stuck with pointing with my mouse, unfortunately. I'll try and get this fixed for the next lecture by complaining to the buildings people. It is a bit annoying. Give me 1 second. I'm getting this feedback. Hopefully this should settle. Okay, so you have the text and a pattern. You start with by putting the pattern against opposing symbols, starting from the first position in the text. You compare X with an A, well, it was a mismatch. Well, there's no point for me to explore if there's a occurrence of the pattern at position 1. You just have to shift right the pattern under the text by 1 position. So that's what you have done. And now the pattern is against the second position in the text. A matches with an A, B matches with a B, and so on until you see matches. But then at some point in this instance, you saw that there was a letter that did not match the pattern, right? Bless you. And then if that happened, well, okay, all this effort was only in vain, because you're looking for all occurrences of the pattern in the text. You could not find that. You had to go through so many matches before you realize there wasn't, it was a red herring. So you kind of move the pattern 1 position to the right, and you kind of repeat the process, and eventually if there is an instance of a pattern in the text, you'd have to compare all characters 1 by 1. So at position 6, A matches with an A, B matches with an B, and so on until Z matches with a Z. Okay? Overall, if you count all the crosses and all the mismatches and matches, there would be 20 comparisons in this naive approach. So early ideas of speeding, and I'm giving you first a hand-waving intuition, and we'll see how various algorithms convert that intuition into a concrete algorithm. So the intuition is that the early intuition is that naive always shifts by 1. So my goal is to be able to have the confidence to shift by more than 1 position at each instance, right? So that seems logical thing to do when you are comparing. If I have the confidence of shifting more than 1 position, then that would save me unnecessary comparisons, right? But then what's the catch by shifting more than 1 position when I have the confidence to do? What is the catch? The catch is that you should be certain that by skipping those positions, I have not missed something between skips. When you skip by 1, there's no such danger, right? So because there's nothing in between if you just shifted by 1 character. But then if you're skipping by more than 1, then what happens if there was an instance in the gaps between the shift? So you want to make sure that the shift is safe. Okay, when you talk about a safe shift, it is a shift where you are certain that there is no instance of the pattern that occurs in the text in between the shifts. Is that clear? Agenda? Anybody is confused? Raise your hands, and then we'll. Are you coming in?
Is it mobile development?
No, algorithms. Yeah. So, okay. So, anybody has any doubts? Please. I really like an interactive session when we can. So, if you feel that something's a bit blurry, put your hand out. Yeah. Feel free. Okay, so let's look at, and again, this is an intuition, it's not a concrete algorithm. I'm just giving you an intuition of what you mean by shifting by 1 position that is safe, a safe shift that is more than 1 position. So let's take this example where the same text, and then you started your first iteration. Well, too bad, the very first character I matched, X with an A, is a mismatch. I have no other possibility, no other sort of information beyond shifting what a naive shift would be. Just shift by 1 position because, well, I just got a mismatch. I've not learned anything so far. And you shift by 1, okay? So iteration 2, going from 1 to 2, is like the naive step, what you had done previously. Now let's see what we can gain in the second iteration for this instance, okay? It really depends on the instance that we're considering, the example that we're considering. So let's say in iteration 2, A matches with a A, B matches with a B, X matches with an X, all the way until, too bad, the very last character, if it were a match, we would have found an occurrence, but then it was a mismatch. So Y matches with a Z, that's a mismatch. Damn, how do we, what do we do from this point? Now, by matching opposing characters in the text, have I learned about the characters that I've seen in the text? Because I'm matching, right? So I'm matching A with an A, B with an B. So I kind of know that if it's a match, the positions opposing the pattern that matched have to be same, right? The letters are the same. So if you look here, A, B, X, Y, A, B, X, until this point matches A, B, X, Y, A, B, X. By going one letter at a time, by doing that matching, I've learned something about the text. Okay? Naive doesn't really record what it has learned about the text. Now, if I have to shift, what would be the most basic thing I want to do? Well, I want to shift such that at least the first letters of the pattern matches to some letter in the text that is opposing it. Okay, when I move, and after shift, at least the first letters ought to match. So, but do I know the first letter of the pattern? Well, I know the first letter of the pattern. Of course, it's A. And while reading so far in the current iteration 2, have I seen an A that appears after position 2? I know that position 2 text I'm using human, I'm counting from 1, by the way, so not from 0, like humans do. So at position 2 in the text, we know that's where we are currently at. That's a shift where we are doing iteration 2. A matches with an A, and you keep going. But the fact that I have read some distance in the text, starting from position 2, I could look for the occurrence of A in the text. So if you look at position 6 in the text, do I see an A? Yep. So if I shifted, the hypothesis is, if I shifted the pattern any position before position 6, after we are at position 2, so in between position 2 and position 6, it will have to start with a mismatch, right? Because they are letters that are not A. The moment I shift there, the first letter would be, well, it's a mismatch. Does it make sense? So I've learned something about the pattern, and I've learned something about the text as well. And in fact, in this instance, you'll learn something about the text and say, well, okay, A doesn't appear in the text until position 6. And how do I know that information? Because I've scanned A matches with an A, B matches with a B, X matches with an X, Y matches with a Y, A matches with an A. So I know that my first letter is an A. I've seen the first occurrence of A in the things that I've read is at position 6. So I can directly jump to position 6. I've saved quite a few of these things. And is it safe? It's of course safe, because in the worst case, I've shifted, and that could still be a mismatch, but I've never missed anything before. Okay, I've guaranteed myself that I've never missed anything before. Does that make sense? Okay. You could do something much more clever, and in fact, this is the crux of what Boyer-Moore does. Intuitively, we'll see the mechanics, the gory details next week. So, well, you could do something much better than just looking at the first letter. Yes, can I help you, sir? Yes, take a seat. Yeah. So we can do something more than just look for what's the first letter. You could actually learn the patterns. So for instance, if you look, so this is the same example. After iteration 2, you have scanned this far. You know that 2 to 8 in the text matches 1 to 7 in the pattern. The 8th character of the pattern does not match the letter at position 9, so Y doesn't match with a Z. But do you see two things here? ABX is the longest suffix of this the matched region. So matched regions are the ticks, right? So if you look at ABX is the longest suffix of the matched region that matches the prefix. Can you see that? ABX also appears here. So there's a prefix of the pattern that matches the longest suffix up to the match. Okay, so the match is between 1 to 7. The suffixes are anything that is from 1 to 7 or 2 to 7 or 3 to 7 or 4 to 7, but there's one suffix, longest suffix ABX, that matches the prefix. And it turns out that if this region matches that region, I can essentially align such that not just the first character, but ABX here aligns with ABX here. And because I know that they are similar, I don't even have to compare those characters, because I've shifted knowing that there is a prefix in the pattern that matches the suffix, and I've shifted such that the prefix now takes the position of equivalent letters under the text. I don't even have to match those characters that I've matched previously in the text. Okay, so and we'll see that this is not yet concrete. It's not, you kind of have an intuition. What does it mean to find the prefix? What does it mean to find the suffix? That's where great computer science comes in. Nifty computer science comes in. Yeah, that's where magic happens. But this is what the general ideas of improvement are. Okay, so with that intuition of where we are heading in the next couple of weeks, we're going to start off with Gusfield's Z algorithm, and before we pick on the ideas we just discussed about how to do efficient pattern matching. Now, I will again reiterate that Gusfield's Z algorithm gives a modern rendition, modern treatment of Boy-Moore and KMP. Clear? Okay. So, down to business. So what is Gusfield's Z algorithm? What's that weird name? Well, it turns out that Gusfield was interested in exact pattern matching, and while studying historical algorithms, he kind of realized that there is some simple data structure that you could construct, pre-process on any string that allows exact pattern matching in times that are linear rather than, so we saw that m times n complexity for the naive, rather than m times n, you could do it in m plus n. Okay? So that's the goal he was chasing after, but he was not keen to fall back on the historical algorithms, but he found something in the process of investigation, that there is this general data structure that reveals very nice properties of the string, any string. So for the first, let's say 50 to 1 hour, next 50 to 1 minutes to 1 hour, forget about text and a pattern. Just think about one string. Okay? We just start to think about one string, and then what does it mean to pre-process that string? And once the pre-processing is off our chest, we'll come back to exact pattern matching and say, how do I use this pre-processing to drive exact pattern matching if you have a reference text and a pattern? Is the agenda clear? So we're just going to look at a pre-processing algorithm and then come back to linear time pattern matching. Okay? So why did he, so what is this fancy name? Gusfield, obviously Dan Gusfield is a very famous computer scientist, made seminal contributions to many areas of computer science, graph theory, algorithmic analysis, string data structures, bioinformatics, I mean, many areas. So obviously, Gusfield sort of honors the fact that he came up with this algorithm. Z is, it turns out that when he was thinking about this, he used Z as a variable name for an array. So data structure that you have for this is an array. If you have a string of n letters, it's an array of n numbers, integers. Okay? The data structure is just an array of integers. So Z was the name of the array that he used. So Zi is the ith cell in that array, ith number in that array. Okay? So Zi values are essentially some integer in that array. Okay? So I'm just giving you some general context. Okay, definition. At this stage, I would have loved to draw something, but then I think I'll try and intuit it. I don't know how I can. Let me just try and if I can still get this back. What is happening? Okay, let me see if there's some connection down there. Now, I can't seem to turn on the document camera nor the smart board, but okay, what is a Zi value? I should be able to, does anybody have a marker? Maybe I have a different idea. Does anybody have a whiteboard marker? None of them. A good lecture theater without a marker. Thank you. Control? Throw it? Yeah. Okay, I can catch. Thanks. I don't know if the people in the stream can see, but what I've drawn is a long horizontal line that is basically mimicking a string, position 1, position n. I'm drawing it, writing as big as I can so that people can, who are looking at the video could.
Can you switch the bottom of the side?
No, I did.
Oh, no, on the side of the wall. There.
Ah, okay, there is. I didn't realize that this was smarter. Fantastic. Thank you, sir. I thought it was only a new. Only the learning and teaching building had one. Okay, so fantastic. We are in business. So if you have a string 1 to n, so as I said, you're storing Z values, which is an array for each position. So essentially, it's an array. Now, at position I, so that's going to be a Z of I or Z bracket Y or Z sub I value, so that's position I. What you're trying to do is what's the longest substring starting at position I that matches the prefix of the same length. So I'll just annotate a substring with a symbol alpha. So what's the longest substring starting at position I that matches the prefix at start? Prefix always has to start from 1, but it has to be of the same length. So if it's alpha is what you have here, it has to be alpha in the prefix. Now, what does longest mean? By what does longest qualify? It means that I could not extend alpha without flouting the match on the prefix side, isn't it? Which means that if there is some character x here, this is some character that is not equals x, right? If it were same, it wouldn't be longest, would it? Because you would extend by one more. So by longest, you're essentially trying to find a substring that matches the prefix such that the characters after that substring are necessarily different. Is that clear? So Zi value is the length is given in that straight thing. So length of, or I'll rather write it much more in plain English. It's the length of the substring alpha. So that region, it's a length, okay? So Zi is stores the length, okay? Is that clear? Okay, now here's an example of a string. Maybe I'll just take this example. Forget about what's on the slide right now, but just stare at the graphic of letters with boxes, because I've drawn a box here, okay? Although Zi is a number, I'm drawing it visually as a box, right? So if you look at that string, can you see that you have certain boxes, and confirm that wherever you see a box, there's an equivalent prefix of the same length that matches with that box. Can you confirm that? Is there anything that you don't understand about that visualization? Yes, sir.
A question about Z6. It's like it's AB and there's an AB.
No. Good point. Let's start with Z6. Good. I quite like when somebody sort of interacts, because it kind of informs more common kind of mistakes that one makes when they're doing it for the first time. Okay, let's look at Z6. So what is Z6? It's the longest substring starting at position 6 that matches the prefix. So A here matches this A. Next one is B matches the next. Does it match, or it's a mismatch? So hence it has to be, Z6 has to be 1. Does that clarify that? I'll take one example, Z5. Z5 is the longest substring starting at position 5 that matches the prefix of the same length. So A matches with an A, the next A matches with the next A, the next B matches with the next B, but the next X does not match with a C. So the Z value at position 5 is 3. Is that clear? Okay, now what happened to Z1? I'm counting from 1, by the way. Yeah. So by definition, Z1 has to be the length of the string, n, right? Why? Because a string is a prefix of itself, okay? Otherwise, we'll get into a lot of set theoretic contradictions, okay? A set is a subset of itself, yeah? So if you basically, a string is nothing but an ordered set, right? Ordered set of elements. A set doesn't necessarily have an order, but a string is a set of elements with a certain linear ordering. Anyway, so what was Z1 necessarily is going to be n. It's the most uninteresting number for the Z array. You don't care about Z1s. Okay? It's meaningless. Or you can start off by putting Z1 initialized to n. It doesn't matter. Okay? But you don't really care about Z1. So you only care about Z2. And then there are places where Z3 is undefined. What do I mean by undefined? So B doesn't match with the first letter. So essentially, the box is undefined. Z value of an undefined box is meaning that the length of the substring starting at that position is 0. Okay? That's what the Z3 is 0. And the box remains undefined, okay? There's no box. You don't see a box, because you can see a box of when there is a match of at least 1 or more, okay? All right, so what does a box mean? By now, at this stage, box means an interval, isn't it? So it's telling you where it starts and where it ends, where the region of match starts. So if I say Z5 is 3, can I immediately tell without any further information where it ends? because I know 5, start point is 5, I know it's 3 characters long, so endpoint has to be 5 plus 3 minus 1. Okay, 5 start point plus length minus 1 gives you the endpoint, right? So essentially what a box is intuitively just an interval. Okay, all clear? By the way, all you need is zi values. You don't need to store the interval, because once I have zi value, I know I have an I have the value of the length at I, which means that I know the endpoint, I know the interval. Okay, you don't need to store that information. All right, so I'll just belabor 2 more definitions before we'll start talking about the meat of the pre-processing and how you could pre-process it. So the next definition is what's called the write values. Okay, now this is a slightly, when you come to it for the first time, it's slightly confusing. Not much, just that the definition of what write is has a small nuance. So let's assume that we have we sort of have at some position I in my algorithm. That means that I have processed everything. I've processed everything from 1 to I minus 1. Okay, I've done everything, the zi value, the z values of everything from 1 to I minus 1 has been done and dusted. We're trying to think from some middle point in the algorithm, right? So, which means that I'm just going to draw some boxes of some lengths, maybe some inside, maybe some overlapping, doesn't matter. They can have boxes that are contained, characters that can overlap, boxes that are separate. Okay, that's the only 3 possibilities you will have. Okay, or perhaps boxes that end at this start at different positions. Maybe I'll draw. Maybe they start at different positions but end at the same point. It really is a structure of the string that gives you the definition of these boxes. Okay. Now you've done everything until I minus 1, or maybe you've finished everything previous to I. Now what is write, the value of write, the R value at iteration I is essentially, it is the, let's also, for heavens, let's say you've finished even the ith iteration. Let's start thinking after you finished ith iteration. So it is the rightmost endpoint of all z boxes at or before I. So there are a bunch of boxes here. Some end here, 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 and now the one at I ends here. So the write definition is not just a function of what you have at I, but everything from 1 to I. So it turns out that that would be the rightmost endpoint of all z boxes that I have seen so far. Clear? Now if I did not have a z box here, let's assume that this character was x and this character was y. Obviously zi would be 0. So what would be the rightmost, what would be the Ri value at that position? So it's the rightmost endpoint of all z boxes at or before. If I didn't see anything here, there's still something that ends there, so that would be the rightmost value of this iteration. Does that make sense? So it's the definition is a function of not the z box itself, but all the z boxes I've seen at or before. Okay? And they all end somewhere, and you're just recording the rightmost one. All right, so, by the way, can I ask you a question? Can, between 2 iterations, can write point of the current iteration be less than the right point of a previous iteration? Doesn't make sense, isn't it? So obviously, it has to be a monotonically increasing number. It always has to be same or more. Because if I had nothing, if my Zi was empty, whatever the previous one would be the same that I'd carry forward. But if I had something at Zi, it would be a number, a right point, the position would be greater than what I had. Okay, it would be same or greater, monotonically increasing. Okay? So keep that in mind because that's a very important observation when we're reasoning about the complexity of this processing. Now, this is perhaps the only tricky part of the definition. The next definition, because we have defined right, we'll define left. Now, left is quite easy, okay? So you have defined right. It is a box that ends at right, isn't it? Some box ends at right. For instance, if there was no Z box at I, the right would be that position, okay? So left would be wherever this, I'll change this to R that way. So left would be wherever it started. So it started out here, right? So left is basically the start point of the box that ended at right. Okay, so it's whatever the corresponding, so you're essentially storing at any position I, the left and right values, in fact, right and left values because right value defines the left value. Yes, sir?
The left point also the rightmost box?
Not the leftmost, no. The left, only the right is the rightmost at or before. Left is, okay, once, so out here, I'll just go back to this illustration. I'll take the scenario where the character here is X, character here is Y, that's position I, so Zi equals 0. Are we on the same page so far? So what is the definition of right here? The right has to be that endpoint, correct? Because it's the rightmost endpoint of all Z boxes at or before. Now, what is the left as L value, the left value associated with position I? It is where did this Z box start? So you're pointing the rightmost to this position. This Z box started here, isn't it? So that would be, now there's one small nuance that I like to flag. There are scenarios where you could have two Z boxes ending at the same rightmost position. So which do you choose? The answer is you don't care. It doesn't matter. The algorithm works even if you choose any one of them, and we'll see what the algorithm is. We are just doing the definitions right now. It does not matter. Okay? So long as you've defined the rightmost endpoint, and if there are multiple left starting point, multiple Z boxes ending at that position, you can choose any one of them. Okay? It doesn't matter. Okay, so with that, introduction, here stated this example, it kind of shows you, for the example that we have stated previously, what the Z values are, what the Z boxes, the interval is. An interval is a function of just the Zi values, right? Interval where it starts, where it ends. And then it also shows you for various positions what the right and left values are. Just try and sanity check that it kind of agrees with your intuition of what right and left is. I'll give you a minute. And if there's something that's confusing you, please raise your hand and we'll clarify. Yes, ma'am.
Before I, there is no Z box.
I'll have to come a bit closer. What was the question again?
What if before I there is still Z+?
Okay. Okay. I think we'll take a case of I equals 4. Okay. Oh, okay. Maybe we'll take a case of I equals 2. Oh, so okay. I think okay. I know what you're trying to say. Let's assume that this character was X rather than A. Okay. Let's assume that's what you meant, right? And then we are looking at position 4. I equals 4, you didn't find any Z box. Anybody wants to have and think about what happens? So Zi is 0, obviously. So the rightmost endpoint it can't be 1. Let's say you're counting from 1, it can't be 1. So you have to have, your programming logic has to capture R as not defined in some way, and not defined can happen if you're counting from 1 if you store it as a 0. If you're counting from 1. What happens if you're counting from a 0? And I'll let you think about how do you store undefined. Okay, it's not defined, right? So there's no right point. There's nothing. The nothing has to be stored as a logic in your program. And if you're counting from 1, I can store 0, if you're counting from 0, can you figure out, it's a good question for you to think into your labs, because the reason I'm doing it with 1 base is because I want you to go back to the lab and do 0-based thinking, because computers always think from your arrays are indexed 0 indexed rather than 1 indexed. And a good way of a good side effect of this is you can't simply translate what you see, you'll have to think about what you're doing. So, and I always believe that process is a edifying process in computer science. Unless you convince a computer, you have not understood the algorithm. It's not me that you have to convince, or yourself, you have to convince a computer. That's why I keep saying this semester after semester, that I believe computers are great bullshit detectors. And I know this because I've thrown a lot of bullshit at it. Okay, so does it answer your question, ma'am? Yeah. Okay, so with that definitions of a chest, we'll try and find out how do we go ahead with the Z algorithm. So Z algorithm is to find out Zi values. Now, in fact, there are a bunch of values that you have to keep track of. Now, Zi box is really not a value that you explicitly store. You know what a Zi box is. It's an interval. Now, you also have this left and right values that you have to keep track of. But the good point is you don't have to keep track of all left and right values. You only have to keep the track of the latest. As you're iterating, only the most recent left and right values. Anything previous, all the values previous to that iteration, I don't care. So for I, you have already computed 1 to I minus 1. Let's assume that you have ended I minus 1. You're going into I, or if you want to like thinking about your finished I and going into I plus 1, it's just a relationship between two successive iterations, basically. So you have some values computed, and you only have to keep track of the latest left and right, because essentially right is monotonic, and everything else is basically straightforward. You don't need anything more before that. Now, naive computation of Zi values, if you think about it, I want to find out Zi values, so at each position you would be comparing the prefix, so that's an n-squared operation, isn't it? So because every time you're doing it, yeah, so that's an n-squared operation. Now, what I'm going to tell you is a method, or what Gus Fields showed us is how to do this in order linear time. Yeah, fantastic. All right. Again, I'm just going to give you an overview of the algorithm. This is a text, serves like study material, so you would see a lot of text, but I'll give you an intuition. So we want to compute Zi values, really Zi values. You only, the idea would be that you don't have to store Z boxes Z boxes can be computed, the interval can be computed in constant time if you have the value of I and value of Zi. If you have at position 5 with Z box is 3, then I'll say that again, if I equals 5 and Z5, Zi value is 3, 5 plus 3 minus 1, start point 5, length 3 minus 1, start point plus length minus 1 gives you the end point. So Z box is basically start point comma end point tuple, so it's easy, you can compute Z box easily from Zi values. You don't have to store left and right for everything except the most recent, which I've already said. And then we will essentially compute the new L and R values for the ith iteration based on by updating the values of the most recent one. And then those will be L and R. So effectively you have two temporary variable left, right, or L and R in your program, and you're just updating them as you're checking along. But you have this array of Zi values that you're filling that you have to remember from whatever you've filled. So that data structure is the Z array. Everything clear so far, or is there any part that you want me to clarify? Okay? Okay, let's start this algorithm from the very first iteration. I'm counting from 1. I don't care about Z1 value. I've already explained why. Okay? I have to start at I equals 2, isn't it? I equals 2, I have no other choice but to do an explicit comparison. What does it mean? I'll go to the board. So what do I mean by that? Is if you have a string 1 to n and you're at position 2, you're essentially saying, does the position 2, that the 2 matches with 1, if the answer is yes, you go to the next one, the 3 matches with 2, the 4 match with 3. So you're essentially comparing letter after letter starting at 2 with the prefix letter after letter starting at 1. You understand that? That's what a Z2 value means. Right? What's the longest substring starting at 2 that matches the prefix of the same length? And when do you stop? You could stop when you find the mismatch, right? So the explicit stops always at a mismatch. Match, 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 match. And the whole idea of a Zi value is that the characters after that Z box have to be different, correct? Okay, so can somebody give me an example of a Z box at 2 that's greater than 1? Any example string where that will be true? Fantastic. And let's say if I continued this like that, let's say that's my string and there's more. So at position 2, what would be the Z box? Z box would be that, isn't it? It's because A matches with an A matches with an A matches with an A, but X doesn't match with an A, stop. And it's good, very trivial to see that there are cases where it will be 0. Let's say it was an X like that, so Z2 would be 0. I mean, it's undefined because I'm counting from, my length is definitely 0, okay? And what, the box is undefined, and you'd have to, because I'm counting from 1, I can call right as 0 and left as 0, okay? Does it make sense? Right associated with position 2. Okay, so if Z2 is greater than 0, it says, once you do explicit matching, so Z2 is the length, right? Z2 means the length starting at position 2. It says set R to Z2 plus 1. What's going on here? So what was the example previously? X, I suppose. That was 3. Z2 was 3. So what would be the right value for index 2, start point 2, length 3 minus 1, 2 plus 3 minus 1 is nothing but 4, isn't it? So the right has to be the right. I'm going to write a subscript, but we can just need one variable called r. We just need a temporary variable because we don't have to index it by any. We know that it's a current iteration anyway. So, but I'll write it as r2 is 4. So I'm writing it as z2 plus 1. What's the logic? The logic is simple. The start point is 2. I mean, I'm counting from 1, by the way. So start point plus length minus 1. So start point is 2 plus z2 minus 1 is nothing but z2 plus 1. That's what I've written there. Okay? And left is wherever that right box started. It started at 2, isn't it? Because that's what you have done so far. And then, and if it is 0, and that explains your question, ma'am, that it's basically defined as zeros, right? Okay, here's a base case where Z2 is 1, L becomes 2, R becomes 2. Is that clear? So left and the right at that up to that iteration is 2 and 2. It ends, the rightmost endpoint of all Z boxes at or before is 2. Where did that Z box start? Well, there's only 1 and it started at 2. So left and right are 2, Z2 value is 1. Okay? Is that clear? Okay, so if I continue with the thinking, now the cool thing about this is I've done with the base case. I'll now start thinking about the general case. And so this reasoning is very inductive thinking, but don't have to worry about induction being scary or anything. Think about this as, well, there's a special case and there's general case, right? The general case, what's the assumption? Let's assume that you're in the kth iteration. I've used I previously. Let's use a different variable now, k. So you've done 2, 3, 4, 5, 6, all the way to k minus 1. You're coming into the kth iteration. Is that clear? That means that all z boxes of 2, 3, 4, 5, 6, all the way to k minus 1 has been computed. And going into the kth iteration, you have stored the left and right values, the rightmost endpoint at or before k minus 1, because you have not yet computed k. You want to compute k, you only completed k minus 1. So rightmost endpoint at or before k minus 1 and its corresponding left point, the left point. So L and R values is what you have. Is everyone clear about the setup, about what we're doing in the general case? Okay, then what are the scenarios? I'll go to the board again. If I exhaust your ink, whoever gave me the pen, I'll replace a new one for you, okay? Okay, so we are at kth iteration. So everything from all the z boxes of k minus 1, so that's k minus 1. So everything from the start to k minus 1 has been done and dusted. You are now at, this is your current iteration that you want to compute. What do you want to compute? You want to compute the z value at position k. That's your objective. Now, there are only 2 scenarios that will arise with respect to where the rightmost endpoint is currently pointing. Okay? So rightmost endpoint could be that your k, so your box, the rightmost endpoint, right could be pointing, could be a value that is less than k. Okay, that's what right is a value that's less than k is case 1. I've said it the other way. K is greater than r is nothing but r is less than k. Yeah. So k is greater than r. Rightmost value is less than k. Can you see that? Now, what's the other scenario that appears? The other scenario that appears is this one. When your right is greater than or equal to k. And so it means that left is here. So I'm just going to remove that for a bit so that it's clearer. So current iteration, so I'm going to call it left. I'll call it right. K is less than or equal to right. Now, can you ever get a scenario where you have k less than left, less than or equal to left, in fact? Why? Anybody?
Is the right endpoint, is the right endpoint of the Z-box is starting out of 4K?
So what right tells you is that what's the rightmost endpoint of all Z boxes at or before k minus 1 in this case, because we have not yet completed k. Because we are doing, so it's sort of a variable that we have defined, right? So it's so previously we were thinking about, we have done I or before, so we have replaced it, that thinking with, so we've done 1 to k minus 1. We have to compute the z value at k. Now, will we ever get a scenario where, so the two cases that I have, I'll maybe draw all the cases in one frame. So 1 n, so that's k. So you could have your right, I'll call it right and left. You could have, that is case 1, case 2, left, right. People don't like me writing right that way, so it's a cursive R. But yeah, so that's case 2. So k can be R, R, all the way inside the box. But I'm considering the scenario where you have a box left, right, so L and R, I'll keep to the symbol, and k. So the question is, this case should never be possible. Why?
Because the left is found at a previous position. The right can be past the k because the box can go past k, but if the left is the start of the box, then...
Exactly. I think you're onto it. So the articulating that answer, rightmost is a function of all the z box I have seen, right? And left would be a left of the z boxes that I've seen. I've only seen the z boxes from 1 to k minus 1, so I wouldn't have seen a z box later than k, at or later than k. I've not yet computed. I'm doing the processing the algorithm left to right. They could exist later on, but I haven't seen it yet. So there wouldn't ever be a scenario where k is less than or equal to the left. Makes sense? Because I've not yet computed the z box at k. Anybody? Yep. Okay. So case 1 is very simple. It's identical to the base case. If my k is after R, I have no other choice but to explicitly compute zk. That means that I'm comparing character at k with the first character in the prefix, the next character with the next character in the prefix, and the next character and the next character in the prefix until I see a mismatch. That's what an explicit comparison is. So that's what you would do naively. So case 1 is a naive computation of zk. Okay? Because I have no other information to go off on. There's nothing that I have seen about the patterns about K, because I've never seen K. Nothing has been covering, nothing that I have sampled previously covers K. It was before, I've not seen anything starting from K onwards, so you essentially have to explicitly compare. So what it's trying to do in this picture is that my R is here, my K is here. There could be more than one letter separating R and K. It looks as if it's the very next letter, but R can be much before that as well, right? So it's K is greater than R is all it's saying. So now to compute the Z box at Z value at K, that character is compared with that character. The next K plus 1 is compared with 2. Then K plus 2 is compared with 3, all the way until I see a mismatch. Let's assume the mismatch is at position Q. Okay? That means that K to Q minus 1 has matched, which means that whatever this length here is same as the substring that appears from between K and Q minus 1 is same as the one that appears from 1 to Q minus K. This width is same as that width. Okay? That's what a ZK value is, isn't it? And then, so if the value of that Z box exists, so it might well be that ZK could be 0, but let's assume that you had a ZK which is greater than 0, then your right has to be updated, isn't it? Because previous right was here. What's my, going into the next iteration, my right has to be updated because I've found a new Z box that ends at Q minus 1. So my right has to be Q minus 1. Does that make sense? Because I got a new Z box. Then what is the rightmost occurrence of all Z boxes at or before? Because I've got something new, the right is updated. Does that make sense? So right is updated. Now where did this right box start? Where's the left? It started at position K, so my left has to be updated to K. Okay, so simple, right? So, and then the only other scenario is when ZK, the Z box is 0, that you didn't find anything. Well, if you didn't find anything, well, what is the rightmost endpoint of all Z boxes at or before? Well, it's whatever it was previously. You don't have to change R. What is the leftmost point? Well, you don't have to change left. So ZK is 0. Okay? ZK, if you start off, you don't have to update at 0, because if you start off an array, you can initialize it all to zeros and then keep updating it to anything greater than 0 if at all you find one, right? So if you don't have to do anything, if you don't find beyond, I've got a mismatch at the very position at the position K, it didn't match, okay? I've done with the iteration, go to the next one, K plus 1. Does that make sense? So we have done case 1. We just have one more case which we have to handle. I think that's the tricky part of this, but we have sufficient time. But let's do some practice on the board. Up. So previously we had done the base case. We got a Z equals 1, right? So at 3, well, which case is that? Isn't it case 1? K greater than R? Case 1? K greater than R? Well, which means that I have to do explicit. Explicit implies that B is compared with an A first. Is that a match or a mismatch? It's a mismatch. So there's nothing that I can do. Z3 is 0, so well, everything remains unchanged. Z3 is 0. Which case is that? Case 1 again, isn't it? K is greater than R case. And then you have to do explicit. C matches with a A. C matches with an A is a mismatch. Sorry, when you compare C with an A, it's a mismatch. It doesn't match, but when you compare C with an A, it's a mismatch. So, well, and then you get to Z, K equals 5. So 2, 3, 4 is over, 5. Going into K equals 5, before you computed K equals 5, your Z box, your R value was 2, your L value was 2, correct? Now you're still again in case 1 where K is greater than R, because when you're starting off computing Z5 value, K is here, R is here, which means that you have no other choice but to do explicit matching. A matches with an A, the next A matches with the next A, the next B matches with the next B, but next X does not match with the next C. So you stop. So which means that Z5 is 3. Now, do you update your R and L values? Yes, you have to. Now the new R would be wherever that box ended. The box ended at 7, so R is 7. Where did it start? It started at 5, so R is 7 and L equals 5. Clear? Okay. Now next iteration. R is 7, L is 5, K equals 6. It's no longer case 1. Can you see? Yep. It has to be case 2, isn't it? All right. This requires some thinking. This is where magic happens. Okay, so how do we reason this? So I'm going to start with something more general, illustration. So we are in a case where K is less than or equal to R, or it's in a box like that. Okay, clear? That was case 2, isn't it? And there are really two scenarios that happen. Okay. Now, if we call this Z box alpha, that means that ZL is the size of that substring. Alpha is a substring. Are you happy with that notation? So the length of that substring is what ZL value is. Did you compute ZL value before? Yes, we already know that value. Now, if that is alpha, do you agree that there will be a prefix of the same length, a prefix alpha that matches that ZL box, right? Characters in the ZL box, we're clear. So would you also agree that there will be a position that will mirror the position K on the prefix side? So rather, if this is L and this is R, this is R minus L plus 1 if I'm counting from 1. Okay, I'm just going to write it. You can check it if that's true. If I'm off by 1, correct me. Okay, so that this width is nothing but this width. Number of characters here has to be number of characters here. The characters have to be exactly same, which means that whatever the displacement of K with respect to L, this position will be with respect to 1, right? However many characters K is with respect to L, the position here will be with respect to position 1. Is that clear? So essentially that has to be, if my computation is correct, it's going to be K minus L plus 1. Okay, that position has to be something like that. So this width has to be same as that width. Okay. Now, have you computed Z value at that position before? There you go. So I want everyone to say that, right? I realize that. You have already computed that, right? So we already computed, we have processed that Z value because we are right now processing here, that's my current position. Now I've already done the Z value there. Now let's pretend the Z box here started somewhere there and ended somewhere here. Let's call this beta, that string beta. So what does beta mean? What's the definition of what does beta mean? It means that this part was beta too, isn't it? So whatever the string is that string. Can you see that? Because that's what a Z box at that position is. Correct? Now, so case 2, I'm actually doing a case 2A if I can elaborate it, because there are many other possibilities of the lengths. So length So essentially, the length of this box could be less than this width, really. So width here is this, right? Whatever is remaining from K to R, that's the width here. That's same as that width here. Beta is of size less than that width. Does that make sense? Okay, so I've already computed this ZL box, and it is less than whatever is remaining in that box there. Okay, so or rather this width here. Okay, so if that's true, okay, I'm just going to clear up some of the annotations. So that's beta. That's beta. So what is the relationship between this character and this character after beta? By the definition of the box that I've already previously computed. Can those two letters after beta be same? They have to be different, correct? Okay, choose some letters. So let's call it X. Let's call it some Y not equals X, right? I'm just going to, it doesn't matter, it's variable, right? There can be some variable X, but there's another variable Y, which is it's a character, and that is a value that's not equals X, right? So it has to be beta X here and a beta Y here, where Y not equals X. It could be any letter, X and Y, any beta really from the alphabet. Can you see that there's an abstraction that you have there? Are you happy with that statement so far? Okay. What would be, so we know that the whole thing is alpha. If that is beta, this has to be beta. Why? No, this is not the box here, by the way. I'm asking, my question is rather, I must actually stop and rewind a bit. I'm saying that this whole string is alpha, and part of the string is beta, which means that whatever the structure here is the same structure here, isn't it? Which means that if I saw beta X, I would see beta X here, and if I saw beta Y at that position, it will be beta Y. Why? Because they are all contained in alpha. Can you see that? Everyone? Which means that what's my goal? My goal is to find ZK value. So what is the relationship of ZK value? It's not a relationship between this and this. It's actually a relationship between this and the prefix, isn't it? It's not the relationship between these positions as much as the relationship between what is the longest substring starting at K matching the prefix. So it has to be a relationship between whatever string that starts at K, what's its relationship with respect to the prefix, correct? So which means that I know that this region is same as that region. I know that betas match, but X and Y's don't match. I can then impose in constant time the relationship between the prefix and the region of interest, the ZK value, the substring that I want to compute. Because beta has to match with beta, but I saw an X, but I have a Y necessarily because this region is same as this region, which implies that we already said Y is not equals X, which means that the longest substring starting at K cannot exceed the length of beta. So we just almost in constant time, not almost exactly in constant time, we know that when the Z box at a position, so this is the position of interest, there's a position that it's mirroring by the definition of ZL, this is same as this K is mirroring that position. I've already computed a Z box here, and if its length is within that width, then I don't have to do anything except copy the Z value of that position on the prefix side. So whatever the ZK minus L plus 1 value would be the ZK value. So what I'm going to show you is the same thing on a slide. So we are computing K. The K is mirroring the position K minus L plus 1. Now the yellow regions are the same, the green regions are the same. These are not, the green is not a Z box yet, it's just a region. The regions are the same, that's what we call, so this, whatever the region is the same. Now, if I've computed the Z box at k minus L plus 1, which means that there is on the prefix side, there is something that's equivalent to the red box, what we call beta in that example. So red is beta, yellow is alpha, the green is a width that we have to contend with. So the red box, the beta, has to be same as the prefix side. The character after beta was x on the prefix, y out here. But we know that because the green boxes are the same, this has to be beta followed by a y, but the prefix has a beta followed by an x, which means that zk at value has to be the length of beta. It can't be more than that. But what was beta? It was nothing but the zk that I've computed previously. So essentially, what we have done is case 2a, where the value of beta is less than the width associated with it. Okay? And you can compute it in constant time. Finally, okay, let's take an example here. Okay, let's take an example here. So Z6 is what we want to compute. We don't know what Z6 is yet. Can you see that the rightmost was ending at 7, the left is 5. So 5 to 7 is same as 1 to 3. Can you see that? So 6 is mirroring the position 2, but 2 had a Z box of 1. Okay? Now, can you see that it had a Z box of 1 because A matches with an A, but the next character B doesn't match with that character afterwards. So we are calling that as X and Y here, right? We just generalized it. Now, it means that if this is AB, this has to be AB because of the relationship between AAB has to be same as AAB, which means that AB has to be same as AB. So if I have to compute a Z box at phi, it's a relationship not between this and this, it's a relationship between the string starting at position 6 and the prefix. But because I have a relationship between this 6, 7 with 2, 3, but then I also have a Z box relationship between at position 2 with respect to the prefix, I can transitively convert the relationship, the Z box relationship at 6 with the prefix. That's the transitivity that I'm applying. So if it's less than that, you set the value, so what we call beta, you set the value to beta, and R and L remain unchanged. Why? Because your Z box is contained inside your Z box. Beta is contained within the left L and R, so rightmost endpoint at or before doesn't change because your new Z box was contained within the previous R because that's the width that you were exploring. Okay? This will be, you will, algorithms have this thing about you get a fuzzy understanding of it because it's an advanced algorithm, but then don't, if it doesn't crystallize, don't worry, your tutorials will sort of reinforce this anyway. And it's important to come to, it's important to think about these algorithms a few times. And then once you have a fairly crystallized version in your head, the test of whether it is crystallized is a computer. So you've got to tell the computer that it's crystallized, okay? So make sure that you practice this. Now, case 2b is a case where, actually I will do it with the slides rather than, so let's do case 2b. Case 2b is when, well, the same scenario, k is between L and R. You want to compute the Z box at k, you don't know that yet. You know that k is mirroring that position, and the Z box previously was contained in the width, But now it can be equal or more. You understand what I mean? So the width is this width, okay? The width of the red bit here is the width between K and R. So previously we assumed that the Z box at that position, so this position here, can you see my mouse? Okay, the Z box at that position is mirroring the position where you want to compute the Z box. Okay, this is what we want to compute. We want to compute the relationship of Zk with respect to the prefix. Okay. Now, what you know is that the Z box here previously was less than or equal to that, or let's say less than that width. Let's strictly say strictly less than that width. We know that what to do, it's going to be whatever Z value that I've computed is copied, nothing changes. R doesn't change, L doesn't change. That was case 1. Case 2 is what happens when that box is equal to or more. Okay? Now, there is, in the tute, I'll get you to think about 2 scenarios separately. I've smashed greater than or equal to. That greater than or equal to implies that the Z box here, starting at that position, is greater than or equal to that width, the width that you see here. That's same as that width between R and K. In the tute, you will see it as equal to case and greater than case. We're going to reason it explicitly, what happens if it's equal to, what happens if it's greater than. I'll convince you, or at least your tutors will convince you, that equal to case requires more work than greater than case. Okay? And you will have to reason that using the same sort of abstractions that we have. I'm just going to keep it at a high level initially, and then once you slow your pace, get a better understanding of what the reasonings of case 1 are, try and see if you can extrapolate that reasoning for greater case and equal to case. Okay? Or do you want me to do one case and then you would do the remaining? Is that also, I can do that as well. So what's the time? 31. I think we do have time. I mean, I will leave intro of the unit, it's in the unit synopsis, but do you want me to do equal to case and then you will do greater than case in the labs? Okay, we'll do the equal to case then. Not bad. Because equal to case is perhaps the most interesting. The greater than case is fairly easy. So L, R, K. So if that is alpha, that is alpha. Are you with me? If that's K and that's L, K and R, that is R minus L plus 1, whatever width here is the same width here, and whatever position here is whatever the number of characters of between L and K is same as the number of characters from 1 to that position, so this has to be K minus L plus 1. Okay? So far so good. We want to compute the Z value at position K, that's your current iteration. What is it is the question. What is the Z value is what you're trying to solve. But you have already computed Zk value at that position. Let's assume that it was exactly equal to that width. That's what we'll handle. This case is handling greater than or equal to. I'll do just one case equal to. Your lab allows you to do greater than as well. If it's exactly same, what does this mean? If this is beta, this has to be beta. That's what the Z box means, isn't it? At that position. So if that position is X, what is that position? Yeah? It's some Y not equals X. Okay, this is important because once we Y is a variable, so some value Y not equals X. Okay? What is this value here? After, at R plus 1. What's the definition of ZL? it matches the prefix. What is the relationship between the character that comes here and y? So there is some z that not equals y. Does it tell any relationship between x and z? So you know that z is not equals y. My question is to be able to compute the z box here. So obviously this value is beta. Okay, because this is beta implies this is beta. This is not the box yet, but if I have to compute the box so this is the region is the same is what I'm trying to say. The relationship with respect to this region and the prefix, so beta matches beta, so it has to be at least beta. Now for it to be more than beta, you have to worry about the relationship between x and z. Do you know the relationship of x and z is a question when without comparing. So can you slow down for a bit? We're good attempt. Please feel. I like the fact that you're thinking through this. So z is not same as y. You said y is not same as z. Then what did you say? Y is not same as x. But transitivity, it is equal to x or not equal to x? It can or cannot, right? So it leaves it uncertain. You only have relationship where it not equal to means it can be anything, right? So you don't have any information, any certainty about the relationship between x and z. You only are certain that y is not equals x. You only are certain that z is not equals y. But you don't know the relationship between x and z is the take-home message. Which means that at this point, when I have to compute zk value, I know that the zk is at least beta log or more because I don't know the relationship between x and y without explicitly comparing them. So I'll have to start comparing them. I have to compare r plus 1 with whatever that character is. So by the way, what is that position? If this position, this width is r minus, so this width, the width here is r minus k plus 1, isn't it? So that width is, so it would be the character after that width. So if it starts at 1 plus width minus 1, okay, so that character has to be r minus k plus 1. So I'm just I'm doing the arithmetic from 1, so that position is r minus k plus 1. Is that what? Okay, that position, so I'm sorry, this position has to be r minus k plus 1. It ends, this width has to be this width, so that position beta ends at r minus k plus 1. So x is at the position after that, r minus k plus 2. I'm counting from 1 by the way, r minus k plus 2. Whatever is coming after beta is that position, and that position is compared with r plus 1. If it's same, the next one, the next one, the next one, until you get a mismatch. Yeah, is that clear? Now, in fact, when you go to the tut, reason why when zk, so when you have a scenario where beta, when you have a scenario where zk minus l plus 1 is greater than that width here. If it's greater than that, strictly greater than, we've done equal to case, but it's greater than, you actually have phenomenal certainty. Reason what that certainty is. It's an easier of the two cases. Okay? Why is it that you get more certainty when you have something longer is what I want you to reason. Now, with that point, the case is, I've just smashed the two things into one iteration. Even though you get greater certainty with greater than case rather than equal to case, you have to explicitly compare as you're doing. So you're comparing r plus 1 with the position associated with x. R plus 1 is compared with, so Z is compared with X first. If it's the same thing, then the position after that, and the position after that, and the position after that, until you get a mismatch at position Q. If you get a mismatch at position Q, then your ZK is basically going to be, you started at K, you ended at Q minus 1, so whatever the width, the length between K to Q minus 1 is, and that length is Q minus K. So whatever, if you take endpoint minus start point plus 1 would give you the length, isn't it? Endpoint is Q minus 1, start point is K, endpoint minus start point plus 1 would be the length, that's going to be Q minus K. R is set to wherever the Z box has ended now, Z box ended at Q minus 1, so that's where it's going to be, and L is going to be wherever it started, that's going to be K, and that pretty much does away all scenarios that could exist in, you can write it in 3 separate cases, case 1, case 2a, case 2b, where it's strictly equal, and case 2c, which is strictly greater than, or you can smash 2b and 2c into 1, as we have done here. So we just call 1 2b, where it's greater than or equal to. It will not change the logic, but then my claim is that if you had strictly greater than, you have greater certainty, and you could do, I think you will save one comparison. Okay? Reason why you will save one comparison, it's not a big deal, but still it's worth knowing that you could save that. Okay? As computer scientists, would like to shave off any optimization that's possible. Okay, so I will sort of, it's an example, more of the same. I'm not going to repeat the examples here. It's essentially showing a scenario that we were exploring, why you have to compare explicit ones. So I'll let you do that in the self-study side. I'll just cut to the chase. So these are just basically some amount iterations going over and over again. So it's for your self-study anyway. Nothing more to be talked about, except we have done how to compute ZI values in all scenarios. Base case, explicit, case 1, explicit, case 2a, free ride, we get a constant time. Case 2b, we get a free ride until certain point up to R, and then we have to explicitly compare after R. Okay? Now, in case 1, all the explicit comparisons are after R, right? Case 1 also, R is greater than, R is less than K was the case 1, or K is greater than R was the first case. And you have to explicitly compare, and you get a new R potentially if there's a Z box of length 1 or more, that it updates R, which means that all the explicit comparisons across all cases have to happen after your previous R. You never compare anything that is within, because everything else is constant time, right? So in case 2a, if you found a Z box smaller than the width, you just copy whatever the Z value of the previous computation is without any further explicit comparisons. In case 2b that we just saw, you only compare the characters after R. You know that it's at least of size beta or more, so you never compare within that width. So you never ever do explicit comparisons in regions that you've already sort of covered in the previous iterations. Now, that kind of gives you an intuition of why it should run in linear time, but let's solidify our thinking about why this computation is in linear time. So, number of iterations. Now, the complexity is a function of total number of iterations plus the number of matches plus the number of mismatches. Now, why did I say plus? Because my reasoning is not about what happens every iteration. My reasoning is about what happens overall in an aggregate way. Over all iterations, there'll be some number of iterations, there's some number of matches, and some number of mismatches. And I've aggregate them and then see what the bound is, and that bound will tell me what the bound of the worst case runtime is. So number of iterations, is that an easy bound? It's basically bounded by the size of the string, isn't it? Number of mismatches, is that an easy bound? When do you stop an explicit comparison? can you ever get more than one mismatch in any iteration? Every iteration has to stop in the worst case with a mismatch, isn't it? You either reach the end of the string or you kind of get a mismatch. So number of mismatches is bounded by n. So in worst case, number of mismatches is bounded by n. The only reasoning that you have to say is what's the bound on total number of matches, not in any iteration. In any iteration, it can be n. So you can have all A's, so 2 can have all. So when you have Z2 values with a string which is all A's, it would be n minus 1, isn't it? Z2 would be n minus 1 because they're all A's. But what happens to R? R will be n, which means that everything inside before R will be constant time computations. You never do any explicit comparisons. Or in other ways, all explicit comparisons happen to the right of the variable R, which is the word right? So, it always happens beyond right. It never happens before right. And what did we say R was? R was a monotonically increasing function, monotonically increasing sequence. You can never get R values that are less in the subsequent iterations, which means that if you're covering 1 to n, you're always proceeding rightwards from 1. You never repeat it. So once you kind of keep going right, and eventually you will get n, you will never repeat the number of matches. So that's total number of matches is bounded by n. So what do I mean by this is the number of iteration bounded by n, the mismatch is bounded by n, the match is bounded by n. That kind of gives you the complexity of pre-processing Z values. I'll just go to so everything what I've said is written here. I just want to stop with the mic drop moment. How do you do pattern matching? So all this is pre-processing. Where is pattern matching in all this? Quite simple. Okay, so it's so simple that it kind of should give you a lot of joy. So knowing this, text 1 to n, pattern 1 to m, I'll construct a string. Okay, I'll construct a string which is pattern, some unique symbol $, text. Okay, I'll concatenate pattern and text. Okay, can you see where this is heading? What is Zi value? It is the longest substring that matches the prefix. What is the prefix? What's on the prefix side? It's the pattern. So anything that matches any Zi value. So if I have a pattern like this, a $, like this, and a text like this. So I'm really interested in Zi values, or rather it is only these values that I'm interested in, although when you concatenate it, you get something like m plus n plus 1, m pattern, n text, 1 symbol in between. So why did I have a $, here? Is because the longest Zi value cannot be greater than m if I have a $, which is unique. Okay? So whenever I pre-process, I compute Zi values of pattern $ text, wherever I see a Zi equal to m, I have I have the substring match the prefix, which is a pattern, occurrence of the pattern in the text. What's the complexity of this? Big O, it's linear. Processing it is linear. I proved that it's linear. Zi. Number of iterations is bounded by m plus n. Order m plus n. Does that make sense? I might have rushed this part, but do you see at least the gist of why if I computed Zi value? So if there is an occurrence of this pattern here, the Zi value will have to be the pattern. Okay, and you're looking for Zi values that are equal to m when you compute the array. Whenever it's m. By the way, a quick tip: you don't need to store ZI values beyond m letters, or m plus 1, so to speak, m letters for pattern matching. You don't need the whole array anyway, because you never get a ZI value greater than that there. And by the way, you could change that without a dollar. You could remove the dollar. It's just that the logic of what it means when you get a match, if you get a match, if the ZI value is greater than equal to m then. Strictly equal if you have a unique character, or if it's greater than or equal if it is nothing separating them. All clear? A bit too hairy, but I guess you will navigate through this. Okay, I think that ends today's topic. Please revise Z algorithm. So the labs are on. There are no labs this week. The lab sheet, the TUTE and prac sheets are already on Moodle. So for the next week, there's no other activity this week except for please prepare. And if there's anything that you don't understand, the forums are on. Answer on the forums, post a question on the forums and we'll jump to it. And make sure that the consultations will be on starting next week. So I'll just leave this week because it's too early. But yeah, from next week onwards, if there's something that you want to drop into a Zoom consultation, feel free and come and clarify. Thank you. I have to give, excuse me, who's, so we want to find out all occurrences of this pattern in text. I will find all occurrences. There could be 1, 0, or 4 occurrences. Construct a string which contains pattern. What is the that would be 1, n plus 1, n plus 2, n plus 3, n plus 4, all the way to n plus 4, n plus 5, which is, so that's n. Now I run a CI algorithm on this string.
Oh, yeah, I see.
Hello.
Sorry.
How are you?
Pretty well.
Going well?
Oh, it's gone the first day, yeah. Got in a bit late, stuck in traffic, but yeah, survived.
You couldn't get, what happened? You were late?
I got late, yeah, I got late because
Traffic?
3 minutes late.
Okay, see you.
I'll play this for you.
Oh,